Oh, oh, great. Robert actually, hey, Robert, Robert actually does have, can be on the chat. Okay, so anyway, as I was saying, so today we're going to do 16.6 and Monday we're going to do 16.7. And I guess it's worth mentioning that now that we're recording to YouTube, hello YouTube, that 16, this is basically the last big piece of theory for the semester. So we'll probably sit on that for a while. And then the rest of the semester is just applications for it. I mean, applications of the main theorem of Galois theory. You could sort of do that your entire life. And actually, as we'll get to, I think I might have we might have maybe a little extra time at the end as we wait for sort of the homework to catch up with the lectures. And so I might talk about sort of Galois theory as it works in my own research, which is not it's not exactly Galois theory. It's a theorem that looks a lot like the main theorem of Galois theory is what it is. Anyway, right. So problem set 9, but it's what passes for a normal Wednesday now. Problem set 9 is due on Monday. We'll have a problem session on Friday from 10:30 to noon as usual. And again, thanks to today's DJ Trent for teaching me also about a new band I'd never heard of, Public Service Broadcasting. Pretty cool stuff. Okay, let's get going. All right, so as we often do these days, I want to start off with talking about Galois theory in a nutshell. I hope this is this font is still big enough for everyone to read. Actually, so I've said the words Galois theory in a nutshell. I've sort of abbreviated this a little, so maybe I can more or less put this all at once, sliding in this giant font. So remember, we're tracking our progress here by saying that the blue stuff is done, as stuff that we've done already, and the purple, or well, I don't know, whatever color this actually is, it's supposed to be purple, is what we're doing today. So again, I guess now that we've defined more terms, I can make made some of this a little shorter. So suppose K is an extension of F, and that is the splitting field of some irreducible polynomial little f in big F, bracket X. So again, we don't think of big F is the ground field. It's helpful to think of it as the rationals, even though that's not the only case that matters. So what we've seen so far is that Galois theory, at least the idea of Galois theory, is that it relates the field theory properties of K as an extension of F, for instance, the degree, and the group theoretic properties of G of K over F. That is the Galois group of K over F, which is remember that it's the group of all. I guess I should just type in a reminder just to see jog my own memory. Remember G of K. I should make this a different color. Put it somewhere else actually. So this up here. Let's make this green. Yeah, there we go. So remember that G of K over F is the group of F automorphisms of K. That's just a little reminder there. So remember that is the group of field automorphisms of the field K that fix every element of F. All right, so again, Galois theory relates the field theoretic properties of K as an extension of F with the group theoretic properties of G of K over F. And we'll start to see a much more precise statement of this, I hope, by the end of today. Anyway, so something we'll talk about, we talked about this partially, almost all of this last time, I think, but we'll definitely finish up this statement today. G of K over F permutes the root. So remember, we're always thinking that K is a splitting field of some irreducible polynomial little f, and right. So the point is that it's always true, even if F is not irreducible, that G of K over F permutes the roots alpha 1 through alpha n of F, and R. This is left over from some sort of grammatical thing. So that's not what I wanted to do. This one, here's what I wanted to do. And is because even a pandemic, grammar is very important. G of k over f permutes the roots alpha 1 through alpha n of f and is isomorphic to a transitive subgroup of Sn. And the transitive, that requires, that's the one place here in this statement where we actually are doing something actually new. We actually sort of talked about the rest of it last week. The transitivity comes from f being irreducible. All right, so just because we're in an emergency in a pandemic doesn't mean I can't be irrationally anal retentive. There we go. Spacing is very important. Okay, so all right, so yeah, so the transitivity, as we'll see, comes from f being irreducible, and the main theorem of Galois theory is what's called the Galois correspondence, and I think we'll get to the end of that today. Maybe not if I keep talking about stuff like grammar, but okay, the idea is that we'll get to that at the end of the day. And then, as we'll see later, and this is sort of what's going to happen after this is up through 16. So this is the main topic of 16.7. Is going to be the main theorem of Galois theory, the Galois correspondence, and then everything else we do to the end of the chapter is the rest of chapter 16. Is sort of leading up to the signature problem of Galois theory. This question of when can the roots alpha 1 through alpha n of our irreducible polynomial little f be written as a function of the coefficients of little f, an expression that uses only kth roots, sort of square roots, cube roots, fourth roots, fifth roots. That's really hard to say, fifth roots. And in some way I mean, the idea is that you want to try to generalize a quadratic formula, because as you may have heard, this was a long standing problem in classical mathematics. This is the search for, people found a quadratic formula, and then a cubic formula, and then a quartic formula, and then people spent forever looking for a quintic formula. And one of the great achievements of Galois theory is to give a good proof of the insolvability of the quintic. Spoiler: there is no quintic formula. Anyway, so that I'll make sure to get to by the end. Okay, so any questions about the big picture? So this is how we begin pretty much every class these days. So everyone ready to move on? Just type yes on the chat if you can. Right. Oh, transitive subgroup. Actually, okay. Let me ask a different question. Does everybody remember? Did everybody do transitivity of actions in 221A? Yes or no? Just say transitivity yes or transitivity no. Yeah, so just actually maybe read the sentence because it's sort of confusing with let's move on. Does everybody remember doing transitive actions in 221A? Say in the chat. Not really. Okay, so it wasn't a big deal anyway. Okay, certainly if it happened, it was not a big deal. So let me say a word about transitive actions, or transitive permutation groups. I think it's probably enough to discuss. All right, so let's see. Let me say a word about. And as you'll see, this is something near and dear and close to my heart. So this is hard to resist talking about this. Transitive permutation groups. It's easier to do an example. I'll do an example. So example. Let's see. 1, 2, 1, 2, 4, 1, 2, 1, 2, 3, 5, 6, comma 4, 5. Okay, so suppose take so here's a permutation group is generated by two elements, 1, 2, 3, 5, 6, and 4, 5 in cycle notation. That is transitive. I'm gonna do an example first, and then I'll tell you the definition. Perverse, I know, but so that's transitive because if we call this thing alpha and beta, because, oops. Because some combination of alpha and beta can eventually, if you do them sort of over and over, and then eventually you'll be able to move any point in. Oh, it's transitive on 1 through 6 on the set 1 to 6, because some combination of alpha and beta can eventually move any point in 1 through 6 to any other point. So that's what transitive means. Here's a non-example. Again, non-examples are actually often more useful than examples. A non-example, if you have G generated by 1, 2, 3, 5, and 4, 6, that is not transitive. Oops. For equals is not transitive on 1 through 6, because it has 2 orbits, 1, 2, 3, 5, and 4, 6. Probably you know what transitive means by now, but I think I should actually write out the definition. So the definition: so G acts transitively on S if comma, for any let's say X and Y in S, there exists some little g in big G such that little g of X equals Y. I mean, it's easier to prove. Let me say, as we'll see later, it's enough to show that this works for one particular X. So one fixed X in S. Fixed X in S, because of what you might call the federal of the FedEx argument. Huh. You know, probably you might not know how FedEx works. So, but I think it's a good enough argument and a good enough name that it's worth. I think it's actually worth being a little bit obscure here. So, does everybody know how FedEx works? I'm actually not curious as I sort of. Let's say in the chat. Just go ahead and say in the chat. Do you know actually how FedEx works as a business, like their model? Okay, so this is like an obscure thing. So I mean, at least this is how it worked when it first started. And it's probably more complicated now. So so the way that here's how FedEx works. FedEx works by saying that every night, how do you get packages from? And this is going to sound weird when I first say it, but how do you get packages from let's say San Francisco to Los Angeles? Well, the nutty thing about FedEx is that everything is shipped through Atlanta. And at least it used to be Atlanta, and probably it's a little bit different now. So so the way that you can get packages from San Francisco to Los Angeles guaranteed overnight, this sort of genius idea behind FedEx, is that you just every night you ship everything to Atlanta, and there's some massive distribution site, and everything gets shuffled around, and then they go back and then they go back on a different airplane to wherever they started. So this is so the point of this, so that's how FedEx works. And transitivity is usually proved in a very similar way. So the way you prove transitivity is that you show that there's some fixed particular place that you can move, call it Atlanta, that you can move everything to, and therefore by taking inverses. So to prove transitivity, it's enough to show that everything can be shipped, be moved to and from Atlanta, so to speak. That is for the fixed X. There we go. There's my 6-minute version of transitivity. So does that make sense? And we will actually sort of use this FedEx argument later on today. So I guess it's worth mentioning. And it's good. I don't know. This is not the world's deepest argument, but I really like it. So does that make sense? Does that FedEx argument make sense? Does both the definition of transitivity and the FedEx argument make sense now? And Robert, go ahead and if that makes sense, please type yes on the chat. This is our class custom somehow now. Yeah. Okay. Yes. That's right. The trivial group is non-transitive on any set of letters with more than one thing in it, and the group generated by a full cycle is transitive, right? Because you can always that's like a lazy Susan. But you can always get the food to somebody else on the other side of the table eventually by rotating enough times. I'm full of metaphors today, or as my family would say, full of something anyway. Okay, so let's get back to Galois theory. Where were we? We're somewhere here. Oh yes, we were proving the fixed field theorem. So this is the recall. Oh yeah, right. I want to recall. So this is what I was calling last time symmetrization. So this is getting your irreducible polynomial by symmetrization. And let's be careful about the hypotheses of this. So let H be a finite group of automorphisms. So this irreducible polynomial over your fixed field by symmetrization. So let H be a finite group of automorphisms of a field K. We're not here mandating that. Excuse me. That we're not mandating here that K be an extension to start off with. They're just it's just a field. And we let F be the fixed field of K. This is all the elements fixed by every the fixed field of H. All the elements fixed by every element of H. So let beta 1 be some random element of K, and look at its H orbit. So this is what I mean by symmetrizing. You'd sort of you symmetrize under the action of H, and that gives you the irreducible polynomial for beta 1 over F, and therefore beta 1 is algebraic of degree R. So in particular, by orbit stabilizer, R divides the order of H. A neat thing. And the proof of the fixed field theorem says, and this is actually half. Turns out to be roughly half of the main theorem of Galois theory, which is that let H be a finite group of automorphisms of a field K, and let F be the fixed field of H. Then K is is a finite extension of F. So that's meant by K over F being finite, and in fact, the degree of K over F is equal to the order of H, which we're going to define here to be n. And last time, we got to the point where we showed that K is a finite extension of F. So is everybody good so far? Oh, questions on the chat? Oh, yeah. Okay. All right. So now that we know that K is a finite extension of F, that a lot of the time, the reason that we're going to want to prove or know that our extensions are finite is that we're going to wait. Is this all I had to do to? Oh my God! I can't believe this is all I have to do. YouTube. I'm so embarrassed to now realize that all I have to do to get a big box is to go sweepy like that, just instead of doing click. Every day is a learning experience. Okay, sorry. I paid $70 for this piece of software. It's a great piece of software, but apparently I didn't bother to read the instructions. Okay, anyway, so as I was saying before I started rudely interrupting myself, the reason that we want to know that K is a finite extension of F is that we want to be able to use this primitive element theorem. So it's because as soon as we have a finite extension, we know that K is obtained from F by adjoining a single element gamma. And I think this is probably not strictly necessary for the proof, but it makes some of the proofs much shorter. It's a good tool. Let's see. Oh yeah. So let K be an element of F of let K be F of gamma, or in other words, let gamma be a primitive element for the extension K. And so I guess I should say here, for sigma in H, if sigma of gamma of gamma, then because by definition H, everything in H fixes big F. Sigma fixes both big F and also gamma. So sigma fixes everything in K. Well, in other words, sigma is the identity. All right. Oh, because H fixes F. Comma. All right. So now so the point is that if we now have realized that the stabilizer of gamma has to be the identity. So this is the only thing that can fix sigma. The only thing that can fix gamma. My bad. In H is the identity. So that means by orbit stabilizer, we know that the order that n, which is the order of H, is equal to the size of the orbit of gamma under H times the size of the stabilizer of gamma under the action of H, and which is it's just this is 1. So this is just the size of the orbit. So n is the size of the orbit of gamma under H, but then we also know, if you look back at symmetrization, one of the things proven by symmetrization is that the size of the orbit is equal to the degree of the extension. Right? The size of the orbit of gamma is equal to the degree of gamma, and K is F of gamma. So this is equal to the degree of K over F, and we are done. Yay! So all right. So what this really means. So this is worth a slogan. Oh, let's see if I can actually do this. Can he do it? Oh, halloo, hooray. Fantastic. Okay, so the point, the punchline of this, Robert, since you haven't been here this last month watching me try to make these boxes larger, you will not believe how happy I am to be able to make the boxes larger without having to fiddle with them. All right, sorry. All right. So the punchline is that Galois, the Galois group G works great, works optimally well for G of K over its fixed field. Yeah, so if you look at an extension of K, an extension, you look at the Galois group of an extension over its fixed field, sort of tautologically, and that works great. Sort of worked optimally. This is as symmetric, optimally. I guess I should say what optimally, as symmetric as possible, with maximal symmetry. Our group is optimal, has maximum symmetry. For G of K, G of K over its fixed field, we will see and actually have seen in our one example of a non-Galois extension that if we G of K over a larger field, is not fixed, is not optimal. Almost sort of tautologically. I mean, but it does not have max symmetry. I guess I should say does not have max symmetry. Okay, but yeah, I don't know. But this is a neat. Well, this is a neat proof in theorem because it's almost sort of somehow or almost tautological in the end. It's just sort of like, well, you know, because we've chosen this extension to sort of be to be over the thing where that doesn't get moved, then you have sort of by definition you have maximal symmetry. I mean, I guess that's the hallmark of any sort of really well-developed theory, that when you understand it, it all starts to seem like a tautology. But anyway, so any questions about the fixed field theorem? No, then I'll just say, are there any, actually, first we want everybody to have absorb the statement of the fixed field theorem. So are there any questions about the statement of what the fixed field theorem says before I just say a word about its proof? I guess a personal word about its proof. Okay, well, the personal word I want to say about its proof is that is the condition of finiteness key. Certainly for this proof, let's see. So which finiteness? I mean, yes. The answer is yes, but let me see. So because I have to say I know very little about infinite Galois extensions. It'd be a very different proof, certainly. It would be a very different proof. You could probably get. So Robert is asking, do we need to find the finiteness of the group of the group H? Robert, is that what you're talking about? Yeah. I mean, they all kind of go together. Well, I mean, certainly this won't work, right? Because there will not, because when you symmetrize, you get something infinite, you get an infinite product. Well, it doesn't make any sense anymore. So So this symmetrization idea goes out. I don't actually know. That's a good question. I mean, what would this actually mean? You'd have to have a different statement. I bet there is something like this that is true, but it would have a different statement, and yeah, because I know that the group theory works correctly. So yeah, probably there's something that's true, and that you'd have to have a different statement, but you'd have to be it would just look very different. You'd have to define maximal symmetry, and probably maximal symmetry, it would just really be tautological then. Yeah, it'd probably be almost tautological, but in a good way, in a useful way. Right, you sort of rig up, what you would do is you'd change the statement of the fixed field theorem so it would match something that's actually true. But I guess that's all mathematics, right? Like, it's all tautologies in the end. Robert, I didn't really answer your question. I don't really know. I'm just sort of bluffing. But is that one of the things you sent me in your email? Robert, is that one of the questions you sent me in your email? My intuition is that a view from a finite. Anyway, I think for right now, what I think is the right thing to say is that I will look it up, and that's a really interesting question. I know very little about, maybe nothing about Galois extensions of infinite degree, and so that's an interesting question. Yeah. Okay. So remind me, especially if you send me your email again, remind me that we had this discussion. I will definitely look it up. I'll probably remember to look it up. It's better than worrying about the rest of the world. Worrying about infinite Galois extensions and infinite Galois groups. Yeah. So any other questions? Actually, let me. I think there were no other questions. So let me actually mention one personal thing that you should that you might have already picked up on. So what you might have noticed that when I started talking about, so this class 221B is, it's algebra, so it's already kind of my native language. And now when I start, you may have noticed that when I start talking about orbit stabilizer and symmetrization, then I really starting to talk about talk in my native dialect of my native mathematical language. So please flag me down, as Robbie rightly did earlier today. If I sort of assume that if I do something like well, of course everybody knows what a transitive subgroup is, because how could you not? That's my entire life. Yeah. So, but yeah, please let me know if I sort of lapse into my own dialect too much. So, any quick questions before we move on to 16.7? Oh, sorry, 16.6. Okay. Yes, that's a really interesting question, Robert, about what happens if you before doing an example. That's right, because I think I signed some of these in the homework. That's right. And with an example, then we get to 16.6. So speaking of infinite extensions, so let K, but this actually will be a finite extension. But I mean, so K let be the field of finite rational functions in one variable. It's just with coefficients and complex numbers. So this is a field that you deal with all the time when you teach calculus or when you teach pre-calculus or college algebra. Maybe not so much in college algebra, but except with complex coefficients. And so we're not, that's an infinite extension of the complex numbers, but what we're actually thinking of it as a finite extension, because we're going to think of it as we're going to look at it as a finite extension over the fixed field under this automorphism. So sigma is taking T to T inverse is an automorphism of K, and is an F automorphism. I guess let me actually blow this back up again. I want to do this. I forgot I want to do this one example. The idea is that sigma. This is unstated, but assumed here. An unstated assumption here. Sigma also fixes F, fixes C. All right. So the idea is that it's the sigma is sort of sends t to t inverse and fixes the coefficients c, and so we let f be let f now be the fixed field of k, the fixed field of h acting on k. So now h. So right. So what did I? So just a well. So what is in h? Well, it's generated by sigma. Well, certainly. So first of all, just out of silliness, the identity is always in h, and sigma is in h because well, by definition of generation. So now what happens to sigma squared? Well, if you look at sigma squared here, sigma squared of t is sigma of t inverse. And then, but if you this is if you algebraically, if you take t to t inverse, you have to take t inverse to t, and so this is equal to t, and so sigma squared is equal to sigma. So sigma squared is equal to 1, the identity element, and so the order of h is 2. All right. So what does this say? Yeah, so we have sort of two theorems going on here. One is that the fixed field theorem says that that the index, the degree of k over its fixed field is going to be 2, and so we're going to the degree of k over its fixed field has to be 2. That's what the fixed field theorem says. And so so we know that it is a fact that f. So now we're going to actually want to find a formula for f, find a generator for f as a field of rational functions. This is a fact. So by symmetrizing, the irreducible polynomial of t over f is g of what variable should, yeah, I guess it should be g of x here. G of x is equal to x. Remember, because remember, the slightly confusing thing here is that t is a field element, and we're having polynomials in that field element, so it's really sort of a two-variable polynomial. So the symmetrization says that we're going to take the product of all the x minus beta, where beta runs over all the elements of the orbit of t, and so that's going to be x minus t times x minus t inverse, and so we get x squared minus t plus t inverse. Look, I can still FOIL plus 1. Okay, so it follows. Oops, no, I can't still FOIL because I messed that up, huh? Let's see if I can do this. Oh, great. I can't still FOIL because I forgot x. Okay, my defense, it's a little confusing having these two variables hanging around here. That's weird. There we go. So if we let u be t plus t inverse, g of x equals x squared minus ux plus 1, and that has to be, and so u is in f, and in fact u is transcendental. There's an argument in Artin to show this. I think it's for t to the fourth plus t to the minus 4, but the same argument will work for t plus t inverse. So u is transcendental. So f has got to be equal to c adjoin u. Yeah, because certainly the symmetrization theorem says this is contained in big F, and if F were any smaller, then yeah, well, yeah. If sorry, I guess if F were any bigger, it would actually be all of K, and so so that's the only option. Oh my goodness, this did not spell very well. Okay, so let me wipe out this thing here. Yeah, there we go. Transcendental. There. Okay. So does that example make some sense? Let me pull back and show everything. So there, I did, you know, God forbid, I did a problem that's kind of like one of the ones in the homework. So does that make some sense? Are we good to continue on to 16.6? Say yes or ask a question. Okay. So, let's start something new. Oh, right. And right, the whole point of this slide is this this one line here, really. I mean, not the entire. And then I'm going to draw a picture. Okay, so definition. So let let K be an extension of F. An intermediate field L of K as an extension of F is a field in the middle. A field L such that F is a subfield of L and L is a subfield of K. You say that L is a proper intermediate field, excuse me, if L is neither F nor K. So if L, all right, so, and the picture that we always got to draw here is that we have the big field up here, and we have the little field down here, and I guess it's helpful to think of, oops, it's helpful to think of, let me blow this up a little, blow this back up again. It's helpful to think of, even though it's not strictly necessary here, that there are going to be other intermediate fields over here. So I guess if you want to sort of concentrate on actually what's going on, just going on with K and L and F, then I think you wouldn't normally sort of fill in, draw these other lines here. But I'm drawing them here because you want to imagine, as will usually be the case, that between any big field K and the sort of base field F, there's going to be lots of intermediate fields in the middle. All right. So right. So right. So I guess what I want to talk about, point out here. So if you have G of K over L, it sort of works here. Those are automorphisms of K that fix L. And sort of, if I look at G of K over F, those are automorphisms of K that fix F. Well, perhaps you saw this already without my having to draw this picture, though I personally find this kind of picture very helpful. And it's certainly useful for later to know how to draw this picture. I hope at least this picture shows that if you have an automorphism of K that fixes L, well, L is bigger than F. So if you fix everything in L, you fix everything in F, which means that that G of K over L is a subgroup so this is very important. So the bigger field, why is it so important? The weird thing to get used to is that the bigger field corresponds to a smaller subgroup, smaller group. The bigger field corresponds to the smaller group. So, and I guess, so let me yeah, repetition is the mother of belief. So I just keep repeating this. The bigger field corresponds to the smaller group. So I guess so one start of the sort of fundamental picture that goes into Galois theory is that F is a subset of L. Yeah, that was not very good. Oops. So F is a subset of L. There we go. But G of K over L is, the inclusion goes the other way. That's a subset of G, or a subgroup actually, of G of K over F. So the bigger field corresponds to the big field, small group. Yeah, the bigger field corresponds to a smaller group. Yes. So this slide is wicked important, as we'd say in New England. Wicked important, or hella important, as they say around these parts. Yeah. So this, and if I hope you remember. Oh, I've done this, except I did this on the wrong side. So if you have seen Galois theory before, the one thing that I hope oh geez, really, not the only thing I hope you remember, but one thing I hope you remember is that I'll type it again. Big field, all small group. That was worth typing twice. I guess I did draw this on the correct side. Oh well. Anyway, fine. So, are there any questions about this? Yeah, this picture here, and this inequality, and this picture in the corner over here. Those are all worth staring at for a minute. So, are there any? Oh, there is a question. Great. Yeah. So in the degenerate case, everything is identity. That's correct. That's right. So you don't really. So it kind of erases this distinction. If in the degenerate case of K equals F, well, everything's trivial, and then well, everything's equal. That's true. That's true. Okay, but are there any other questions about either this general picture of the intermediate fields between K and F, and the fact that the idea behind this inequality here, and especially this picture, the start of this the Galois correspondence picture over here in the corner, because that's worth meditating about. And let's meditate for 10 seconds. Om. 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 Yes, that was worth meditating about for 12 seconds. Okay. So I'll take it that everybody's good, and we'll move on. All right. So now I'm going to now prove sort of another. I think this is actually the other part, basically the other half of the main theorem of Galois theory. So suppose K is a finite extension of F, and let G be the Galois theory of. Let G be the Galois group of K as an extension of F. Then the following are equivalent. So K is a Galois extension of F. That is, it has remember this means maximal symmetry. We've already sort of stated. K is a Galois extension of F if and only if F is the fixed field of G, the fixed field of G, if and only if K is a splitting field of something over F. So Galois extensions are the same as splitting fields, are the same thing as saying that the fixed field is as small as possible. There's like nothing else. So this by definition, K must fix. So by definition, so if G is the Galois group of K over F, then by definition, G fixes everything in F. That's because this is the group of F automorphisms, and condition 2 says that there's nothing else going on there. Okay, so that is what that is the character. This is sort of the main theorem. Well, it's not sort of. This is the main theorem, section 16.6, and so that's what we're going to prove over the next few slides. Maybe we might have to finish the proof on Monday, but that's fine. Well, actually, yeah. Let me pause here. So, are there any questions about the statement of that theorem and sort of what those three conditions mean? So, being a Galois, 1, being a Galois extension, 2, having a sort of the smallest possible fixed field, given that you have a group of F automorphisms, and 3, K being a splitting field over F. Okay. All right. So let's talk about the lemmas that we're going to need to prove this characterization of Galois extensions. So first, the first lemma is actually just I'm just restating the fixed field theorem that I said before. So if H is a finite group of automorphisms of some field K, then K over K to the H is Galois, and H is equal to the Galois group of that extension. And so that's just the fixed field theorem. So lemma number 2, and this is slightly reordered. I mean, I'm really just taking this. I tend to stick to the book, as you know, but these are really taking the structure present in the book. So lemma number 2 that we're going to need for the proof of the characterization that Galois equals splitting equals smallest possible fixed field. Right. So, but the characterization theorem. So, right. This is the second lemma that we'll need for that is that suppose K is F adjoin gamma 1, and let F be the irreducible little f be the irreducible polynomial for gamma 1 over big F. And let gamma 1 through gamma r, right, which we are not assuming is the fixed field of K. So let gamma 1 through gamma r be the roots of little f in big K. And this is sort of. So this is, you may recognize this as this is kind of a, transitivity. I hope you can sort of see this is like related to a transitivity argument. So this is transitivity, where gamma. I'll move this box later. Gamma 1 is Atlanta. Let's see if I can move the box here. Move it up a little, maybe. Where's my arrow tool? All right, yeah. So the point is that this statement here is really this stuff over here, this point over here, is really some kind of transitivity statement, right? There's something that sends gamma 1 to each of the gamma sub i's. But actually, this is even a more specialized statement where you have transitivity, and the stabilizer of gamma 1 is trivial. That's sort of coming in the unique sigma sub I. Anyway, so there exists. So if gamma 1 through gamma are the roots, then there exists a unique sigma sub I for every for every I from 1 to R, there exists a unique gamma sub I such that gamma I of sigma I of gamma 1 is gamma I, and it then follows that G of the Galois group of K over F is equal to it has order R. It contains exactly these sigma sub I's. All right, so that's lemma number 2, and so hang on a sec. All right, so sorry, had to mute for a minute. Okay, so all right, so right. So if K is a finite extension of F, so this the degree of K over F is less than infinity, then we say that then it follows in our third lemma that G of K over F has to be finite and must actually in fact divide and oops. My bad here. Then the order of G, the Galois group of K over F, is finite and must divide the degree of K over F. So again, lemma 1 is the fixed field theorem, and we're going to prove the other 2. So is everybody good with a statement of those 3 lemmas, especially 2 and 3? I mean, because 1 is actually not new. Okay, so let's go ahead and prove them. All right. Okay, so lemma 2. So we want to show that if K is so F adjoint gamma 1, then F is then F is the and so so suppose K is F with a single element adjoined gamma 1, and suppose F is let little f be the irreducible polynomial for gamma 1 over big F, and so let gamma 1 through gamma R be all the roots of F and K. So there exists we want to show that there exists a unique sigma that sends sigma I that sends gamma 1 to gamma I, and therefore that therefore that the Galois group of K over F has order R, and it contains exactly these sigmas. Okay, so first of all, nuts, I forgot this. So let's see. Let's sweep this out like this. Great. First, we know that that G of K over F must permute the roots of F contained in K. Because we know that that F automorphisms preserve the roots of a polynomial with coefficients in big F. So that's the first thing to realize. Second, we know that we know that and let me put this in terms of let me switch the pen here. We know that F we know that, sorry, let me go back and put in something over here. We know that comma, because F is irreducible, going back to the pen, F adjoined gamma 1 is isomorphic to F bracket X mod little f, which is isomorphic to F of gamma R. So abstractly, F of gamma 1, which is K, right? So K is abstractly isomorphic to isomorphic to f of gamma gamma sub r, gamma sub I. I should make that an I, not just the last one, but any of those roots gamma sub I, and so K is isomorphic to one of its subfields, f of gamma sub I, which means that K must be actually equal to that subfield gamma sub I by a degree argument, for example. Oops. Right. It's like it's sort of like saying if K, it's like saying if a group is isomorphic to a subgroup of the same finite order, then it must actually be equal to that subgroup. Right. So that means that so there exists an isomorphism, an F isomorphism. There exists. So there exists an F isomorphism sigma sub I from K to K, such that sigma sub I of gamma 1 equals gamma sub I. Well, that's it. That's what we want. So there exists so there exists right. Oops, and then I didn't leave quite enough room here. So then the rest is not so bad. The uniqueness of sigma sub I is because K because an automorphism. I need more space here. So let me actually get rid of this. Okay. So sorry, I didn't leave quite enough space here. My bad. But so then the question is, why is this unique? This is unique this is unique because an F automorphism is determined by the image, by what it does on gamma 1, and so we just said what happens. We said, but sort of by the hypothesis that on sigma sub I that gamma 1 has to go to gamma sub I, and so there's only one that can possibly do that, and then to get that that the order of G of K over F is equal to R, then that these sigmas are exactly all possible Galois F automorphism of K. Well, that follows because that's orbit stabilizer. It's always orbit stabilizer. My class is always orbit stabilizer, by God. Orbit stabilizer. Because this uniqueness statement says that the stabilizer of gamma 1 is the identity. All right, so sorry, minus 5 points for formatting, but I think I hope at least plus 1 point for the argument. Sheepish grin, but still happy. So is everybody good with lemma 2 and its proof? Say yes in the chat. Yeah, I think mostly it's these last two statements aren't too bad, but the most of it is remembering that f of gamma 1 is isomorphic to f of gamma I because little f is irreducible. Okay. Wow, I didn't leave enough space here at all. Maybe I meant to. Let's see what happens. Suppose K is a finite extension of f. We want the next thing to show is that G is the order of. Let's see the order again. The order of G. Oops. The order of G. Which is the order, in other words, the order of G of K over F is finite and divides the index of K. Sorry, I want to say index because I'm at heart a group theorist, not a field theorist. But okay, I want the degree of K over F. Right. So yeah. So we want to show that order is finite. In fact, divides the degree of. In fact, divides the degree of K over F. All right, so so first of all, we know that G has to be finite because so for example, we can take K to be F adjoint gamma, that's the primitive element theorem, and apply part 2. There are only finitely many roots that are possible, and so the order of G must be finite. So this thing makes sense, and now we can apply the fixed field theorem. So by the fixed field theorem, oops. By the fixed field theorem, which we can now apply because G is a finite. The order of the Galois group of G over its fixed field is equal to the order of G. That's what. Oh, sorry, that's not the fixed field theorem. My bad. The fixed field theorem says the order of G is equal to the degree of K over its fixed field. My bad. Let me just go back and make sure that's actually what the fixed field theorem says. All right, the fixed field theorem says, yeah. Oh, the fixed. Yep, fixed field theorem says that the order of so we have a finite group of automorphisms of group K, and says that the degree of K over the fixed field is equal to the order of the corresponding the sort of input group of automorphisms. That's what we have here. So by the fixed field theorem, the order of G is equal to the degree of K over the fixed field K to the G, and then the other observation is that K to the G is an intermediate field. So the degree of K over F is equal to the degree of K over the fixed field times the degree of K over the degree of the fixed field over F. And so, well, that's it, right? So we know that the degree is we got that G is a finite group, and yes, in fact, this is the order of G, and so oh my goodness, my handwriting kind of deteriorated here. Yeah, so there we go. The order of G divides the degree of K over F. Whew. All right. Questions. So let's pull back and look at actually let's pull back and look at these three lemmas again. So questions. Any questions about those three lemmas? And so they're there. Actually, and the first one's just actually let me pull back to whole page, so you can see the whole page. So are there any questions about the first lemma, which is the fixed field theorem, or either of these lemmas? Okay, so all right, so I think we probably have just enough time. Yeah, we do not really have enough time to prove this, I don't think, but maybe we can do the first step. So again, the characterization of Galois extensions, which says that Galois extensions are the same as the extensions with the sort of smallest possible. I mean, it's a little weird because you want to think of having sort of the biggest number of symmetries is the same as having the smallest possible fixed field, given that you have the symmetries. That there's no, I guess maybe smallest possible fixed field isn't quite the right way to say this. There's no surprise elements in the fixed field of G, no extra elements in the fixed field of G, no extra elements, I think is probably a better way to put this. No extra elements in the fixed field of G as the Galois group of G of K over F, and that K is a splitting field. Okay, so I guess okay, we may have just enough time to explain the equivalence of 1 and 2. So let me just do that quickly. So that's it. And why is 1 equivalent to 2? Well, if you look at if you think of the fixed field, so we start off with the Galois field, the Galois group of K over F, and we look at the fixed field of that group G. Then we know. So yeah, let me just maybe elaborate this on this a little bit by the fixed field theorem, the sort of use of FFT in this class. That implies that that the order of G is equal to the degree of K over the fixed field, and so that so this term over here is equal to the degree of K over F by the usual multiplicativity theorems, if and only if the order of G is equal to, well, not by multiplicativity, but almost as a tautology, K over F. All right, something like that. Okay, so I hope my new. So how distract? So let me ask you guys. So sort of go 2 minutes over here. So let me ask you guys. In my new setup here, how distracting was the background noise? A little bit, not at all, or kind of distracting? Did everybody hear the background noise? My daughter complaining about her 4th grade class. Huh. Robert says the background noise is not distracting. I don't know if it's okay. And you go ahead and complain if it was distracting, because we can sort of fix it a little. I can take some steps to try to fix it a little. So everybody's okay with it? You know what? I'll have to listen to the last 20 minutes on YouTube, and we'll see how that goes. All right. I think it's maybe only distracting to me, and I think the mic is pointing in a direction where you can't really pick it up. Okay. So thank you very much. I'll even turn on my camera. Thank you very much for coming. Goodbye, YouTube, and take care, everybody. Bye.